Greetings and welcome to Unit 9, which is on the death and life after death of stars. In this first mini lecture, we are going to talk about supernovae. Before we begin talking about supernovae, though, I want to remind you of the very last stages of the life of a massive star and what touches off the explosion. So even though we went over this slightly during Unit 8, we'll just remind you of this and then we'll continue on. So at the very end of its life, a star that is at least 8 times the mass of the Sun looks a bit like an onion. At the center we have an iron core, and around that several shells of various fusion reactions that are going on, with the outermost shell being hydrogen forming into helium, and then that helium can then fuse into heavier elements all the way up to iron. And then the outer parts of the star, it's a red supergiant star, so the outer parts aren't shown here, but that's still a lot of mostly hydrogen with a little bit of helium extending out several astronomical units. We also talked about how once the core forms iron, it's no longer possible for the star to get energy out of fusion. If you remember this graph, the lower we go on the graph, the more energy we get out. And once you hit iron, you're at the bottom of the graph. If you try and fuse to heavier elements, it will cost you energy. So fusion will stop at the core of the star, and gravity then begins to pull in. Because remember, the entire star's life is this balance between gravity pulling inward and pressure due to heat from fusion reactions pushing out. Once there's no more heat to be gained from fusion and fusion stops, then gravity begins to win. In a low mass star, we got a white dwarf, and this was because when gravity tried to squeeze the carbon and oxygen, we reached a point where the electrons were rubbing shoulders. This was what we called electron degeneracy. You can't put 2 electrons in the same place at the same time, and so gravity was forced to stop by this pressure. But in a massive star, gravity is sufficient to continue squeezing, and the electrons just give up. They merge with the protons to make neutrons, and now all that space that the electron took up is suddenly available, and gravity can squeeze all that space out of it, and you get what is basically a giant atomic nucleus out of what used to be iron. So since this central part has now collapsed inward very small, all the layers above it no longer have support, and they begin to collapse inward. When they hit this giant atomic nucleus, these outer layers bounce outward. That sets off uncontrolled nuclear reactions, and we get an explosion called a supernova. A supernova is bright enough that for a short period of time, the supernova outshines an entire galaxy. So here's an example. This is a picture of some stars in a neighbor galaxy to the Milky Way called the Large Magellanic Cloud. And the arrow points to a star. So this is a picture from early 1987, and that star, it's still alive. So the gentleman who took this picture, his name was Ian Shelton. He was an astronomer at a telescope in Chile, and he was taking pictures of regions of this neighbor galaxy of the Milky Way. And shortly after he took this picture, he took another exposure and saw this instead. Saw this very bright star where before there was just a normal one. This is not a star, this was a supernova. And this was the first supernova to be visible to the naked eye without a telescope since Kepler in 1604. Because supernovae are so bright, because they can outshine their entire host galaxy, we can see them from long distances if we happen to be looking when one goes off. Now a supernova lasts from a few weeks to perhaps a few months if it's relatively nearby. But even then, if you aren't looking at that galaxy, which sometimes you can go months without looking at a galaxy, you might miss the entire event. So on the left here is a nearby supernova that went off in a relatively nearby galaxy, if you call 55 million light years nearby. But on the right are 2 pictures taken by the Hubble Space Telescope about 7 years apart. And if you notice on the rightmost picture there's a faint red dot. next to that central galaxy, and you look in the left picture taken 7 years earlier, and that red dot's not there. That is a supernova in a galaxy 8 billion light years away. That little smudge that it's close to is not the host galaxy. The host galaxy is so faint we can't even see it on the original Hubble Space Telescope image. On average, a typical galaxy has one supernova about every 100 years. So once the supernova happens, those outer layers of the star are flung off at thousands of kilometers per second. This is a good fraction the speed of light. This movie that you're seeing is a picture of supernova 1987A. The ring is not material that was thrown off by the supernova. It's a ring of material that the star ejected several hundred years ago. And you can tell when the blast wave from the supernova hits this ring by when it lights up here. And this ring is a few light years across, and the movie you're seeing lasts about a decade or so. So the blast wave is able to get to this cloud of material in a very short amount of time after the supernova. Now, if you notice, if you look at the dot in the center, that's the remains of the exploded star. And as you watch this movie, you can see it. First it fades away as the supernova fades, but then you can see that purple blob in the middle getting larger and larger. That's the shrapnel from the star itself, from the explosion itself, spreading outwards, again at thousands of kilometers per second, very fast. This material keeps expanding, and as it expands outwards it begins to cool off and become more and more tenuous. So here are two supernovae that were in our own galaxy. On the left is the Crab Nebula. This is a supernova that went off in July of 1054. It was seen by Chinese astronomers near the horns of Taurus the Bull. And when we look there today, we see this shrapnel from the star that exploded almost 1,000 years ago. On the right is a supernova called the Vela supernova. This explosion happened in prehistory. Our ancestors almost certainly saw it. It would have been nearby enough. It would have been as bright as the full moon. But because it was before written records, we don't know exactly when it happened. But you can see there that the material of the star has spread off and cooled enough that now most of it's invisible. A little of it is still visible, and this is now many, many light years across. As a supernova expands, the gas cools off, and it rejoins the interstellar medium, gets mixed in with that dust and gas that we talked about a couple units ago, and it will be reformed into new stars, recycled into new generations of stars. For the Crab Nebula, we can actually see it expanding. Here are two images taken 30 years apart. There's the first one and the second. The first and the second. And you notice that a lot of the tenuous material expands between the two. Some of the fainter regions we don't see just because of a difference in exposure. But you can actually see this getting larger. Using these two images, we can get a constraint on when the explosion happened. Now we know when it happened, but we can confirm that here. We see the material flying outwards. We know that there are 30 years between these two pictures, so you measure how fast it's flying out and run the clock backward to see when it was all in the same part, and you get in the middle of the 11th century, which is when we actually saw the explosion. So that confirms that what the Chinese astrologers saw is what made the Crab Nebula. So this is the story of a supernova. A massive star explodes, part of it implodes inward, and we'll talk about what happened to that part in the next couple of lectures. And then the rest of it is blasted off into space where it cools off and is recycled into new stars over tens of thousands of years. So let's talk about one important thing of supernovae, and that's where do elements come from? So later in the class we'll learn that the Big Bang only made 3 elements: hydrogen, helium, and lithium. And of those, we are made of hydrogen in the sense that water contains hydrogen, but we also are made of many other elements: carbon, calcium, oxygen. Where did those come from? They didn't come from the Big Bang. So the production of new elements is called nucleosynthesis. And if we remember, a sun-like star made up to carbon and oxygen, but the carbon and oxygen fused in a sun-like star goes into the white dwarf, and the white dwarf sticks around. It doesn't dissolve over time. So that carbon and oxygen is stuck inside the white dwarf. Massive stars make all the way up to iron, and you think, great, yes, lots of iron around us. We use it in building our cars and ships and everything else that's metal. So it must have been made in the core of a massive star. But that iron goes into the neutron star or the black hole. It doesn't come out into the universe. So where do we get all the iron? Where do we get all the carbon and oxygen? The answer is from the supernova explosion itself. So again, with just the Big Bang, here's the periodic table, all the elements in nature, and everything up through, from 1 up through 92, which is uranium, 1 is hydrogen. All of those elements occur in nature. All the elements more massive than number 92 are produced in nuclear reactors on the Earth in labs or in nuclear power plants. They don't exist freely in nature. Here is a plot. This is kind of a complicated plot. Let's not get lost in the details, but it basically shows how much of each element there is in the solar system. And this plot, so the y-axis up and down tells us how much of stuff there is. So if you look here, you see that on the far left, these are the light elements. Hydrogen and helium are up really high, and then you go down to get to oxygen and carbon. That's a difference of a factor of 1,000. So there's a huge scale on the up and down. The main thing to notice is that as you go from the low mass elements on the left to high mass elements on the right, they generally get less and less abundant. So hydrogen's the most common, helium's second, we've known that. Then you get to carbon and oxygen and keep going down to Ca, which is calcium, and then it continues to go down until all of a sudden it jumps back up for iron. Then it goes way down again until you get to tin, then up to barium, then back down to get to platinum where there's another jump, and lead where there's another jump. So important thing, don't get lost in the details. The light elements are very common, and then you have a few peaks of elements like calcium and iron and tin and lead, but otherwise most of those elements are not very common. So as the shock wave of the supernova goes outward through the star, I already said that we get uncontrolled nuclear fusion. And this is a process called explosive nucleosynthesis. And so as the blast wave goes through all the layers of the star, these onion layers of the massive star, in the silicon layer we can get fusion into iron. Actually, we fuse into nickel, and that's radioactive and decays into iron. But we get lots of elements around there: iron, nickel, copper, chromium, a few other things around iron in the periodic table. So one reason that you see a peak there at iron in abundances is because those are made as the blast wave goes through the silicon layer of the star, and that is expelled out into space. Other explosive nucleosynthesis elements tend to be even-numbered elements from helium up through titanium. So even numbers are like carbon, oxygen, neon, calcium, titanium. Go back to the periodic table and you'll see every other one gets filled in. So when we take these two things, making elements around iron and making the even-numbered elements, we now can explain where the colored-in elements here come from. The yellow ones, hydrogen, helium, and lithium, come from the Big Bang. The blue ones, those all come from explosive nucleosynthesis. But you see, we still have a lot of the periodic table that's not filled in. Where do those come from? Well, the other elements are made mainly by atoms capturing neutrons. And there are two places that atoms can capture neutrons. The main one is near the neutron star in a supernova. So we've made a bunch of neutrons, that big ball of neutrons that used to be the iron core. A lot of those neutrons are kind of flying around, and they can get added on to elements like iron. And this happens very fast, in a matter of seconds. And since it's so fast, this is called the rapid process or the R process. And then in red supergiant stars, there are a handful of very rare nuclear reactions. They rarely happen. And so an atom that's there will get a neutron now and then. And this way of making elements is called the S process because it's slow. You may get one neutron a decade or one a century. These two processes, the R process and the S process, make almost all the other elements in the periodic table. So this means that you are made of stardust. Everything in you that is not hydrogen, helium, or lithium, which frankly is most of you, came from supernova explosions. So here's the summary. What should you know about where elements are made? First of all, there's this big word called nucleosynthesis. That just is the creation of new elements by fusion. And the elements that were made by fusion in the main sequence, in the core of the star, the carbon and oxygen in a low-mass star, or the iron in a high-mass star, those don't go into space. Those get trapped in the dead star, in the white dwarfs, in the neutron stars, in the black holes, and don't get out. So carbon and oxygen and iron, though, they're very common elements. And where do they come from? They come from nucleosynthesis in a supernova. That blast wave causes these elements to be formed. And a lot of those are the even-numbered elements in the periodic table, and iron and those around it in the periodic table. Whereas all the heavy elements and most of the odd-numbered elements come from the capture of neutrons in one of two places, either in a red giant, where you occasionally get a neutron from some rare process. This is what we call the slow process or the S process. The other place you can get neutrons is in a supernova right near that neutron star. Elements can capture a lot of neutrons very quickly and go up and become things like uranium and lead and other very heavy elements. So this concludes our mini lecture on supernovae. You may now proceed on and complete the response questions.